I would leave it on so that people can.
So people can see me, so it's not actually on. So on the video on for me, and then I can talk into people rather than talking. Okay, well that was easy. Thank you for that kind introduction. It's really nice to be back. Sorry, Brexit's still happening. There's nothing I can do about that. Okay, now can you see my face?
Yes.
Okay, brilliant. I'll try not to move around. Nope. Yeah, we're now having more technical problems. Okay, fabulous. Okay, so how to build a human chatbot. Let's just get starting. Jason, you'll tell me if I move too much and my head goes out of the screen, so I haven't got myself on the screen. Okay, so I'm not actually going to talk about how to build artificial chatbots, as somebody thought last time I gave this talk. I'm going to talk about how to build humans. But I am going to start with a comparison between humans and chatbots. So here are AI chatbots. Here's some little cutie human chatbots. And children and machine both learn human language, and they do, right? So whatever else you think of LMMs, it does look like they are building structured linguistic representation. So they're not using some heuristics. They're not just memorizing what they know. They are learning language. So on a superficial level, human chatbots and artificial chatbots kind of do the same thing. So lots of language goes in, and with some chatbots, artificial visual input. They do some sort of structure building, learning, building representations, and then lots of language comes out. So there is a similarity in the sequence or at a superficial level. But there's at least one big difference between humans and machines. And I asked, and it's the rate at which they learn language. So I asked dear old Claude.ai how long it would take a human child to learn language if it learned at the same rate as GPT-5. Assuming children are learning from 10 hours of spoken input a day, because they're asleep a lot of the time, taking into account the average rate of child-directed and child-surrounding speech per day. What do you think the answer was? How long would it take a human child to learn language if it learned at the same rate as GPT-5? Any guesses?
100.
Hundreds of years?
1,000 years.
1,000 years? Claude told me it would take between 3 million and 8 million years for a human to learn language if it learned at the same rate as GPT-5. So this is the best way I have found to make it quite clear how super efficient human learners are compared to even the best artificial language systems that we've managed to create. So if humans learned a language at the same rate as ChatGPT, we would all be long dead, way dead, long before we learn language. So what is so clearly we're learning in a very different way. And there's a number of reasons why humans are such efficient learners compared to GPT-5. And it's to do with the way that we learn language. So this is the article that Patrick was just talking about with the Lucid directors that we published last year. And this is how we've been conceptualizing what the language learning process looks like on the basis of accumulated evidence over the last few decades. And this is what we call the feedforward-feedback process of language acquisition. So first of all, we have these feed-forward loops. So information coming from the multimodal environment goes into the child's learning and processing mechanisms, and then they build representations of knowledge out of that structure building process. So they're building these structured representations. But at the same time, you also have feedback loops like these ones, where because linguistic representations are sort of built iteratively on earlier knowledge that the child has gathered. So at the point of learning, what children are learning is both what's coming into the input, but they're also interpreting it in terms of their former knowledge, so everything they've learned beforehand. And this affects both the input, so how much a child knows affects how they behave and affects the interaction, but also it actually affects sort of the active adaptive learning process. And there's a couple of key differences between the human chatbots for the kids and artificial chatbots like GPT-5 here. First, focusing on this middle part of the diagram, some of the differences in the learning and processing mechanism. So human learning processing mechanisms have way more parameters, even than the millions of parameters that GPT-5 has. And also human brains have some sort of innate constraints on learning. So very minimally, for example, they can distinguish speech from non-speech. We know children do that from very, very early on. So they don't interpret patters and bangs from a car noise as if it's speech. So they have some sort of innate constraint. Now, I'm not going to talk about this today, but we can talk about it in the Q&A if you're interested in what we think about what the structure building process is. Another difference is how they use their knowledge to sort of affect the learning process. So what children already know doesn't affect just how they interact, but it actually also affects the speed and the efficiency of the learning process itself. So you get this sort of virtuous circle. The more you know, the faster you learn, and that just sort of rolls. And this is to do with how advances across the whole cognitive, socio-cognitive, perceptual system, all of these things as children develop allows them to become more efficient language processors. And again, I'm not going to talk about that bit today, but we can talk about it in the Q&A. What I am going to talk about is this bit, big differences in the environment between what human chatbots are, the environment from which human chatbots are learning and the environment to which GPT-5 is learning. This is the goal of today's talk. Okay, so this is the input that we give GPT-5 or Claude or all of the chatbots. It's just vast amounts of text just fed in, sort of brute force statistical learning. But humans learn language this way, in hours and hours and hours of social communicative interaction. And this is one of the things that really makes the difference. So this is what multimodal interaction looks like. Hopefully sounds like. Mm-hmm. Okay. It's not working. Maybe not.
Hit the play button. The play button.
Very good. Still getting the feedback.
Use this one. Give me a kiss. Oh. What's this one? What's that? Horse. You give me a kiss. Oh. What's this one? It's chicken. Give chicken a kiss. Oh. And what's this one? What's this one? What's this one? A sheep. Oh, yes. You're going to give the sheep a kiss. Oh. And what's this one's my favourite here? What's that? Yeah. What is it? It's a cow.
Okay, so that's quite enough of that. Lots of kissing, lots of cows, lots of bars. So this is how children learn language, and this is different from how large language models learn in at least two ways. The first is that this is not only multi-layered input, so with information coming on from frequency, from paucity, from phonology, from meaning, but it's also multimodal input. So the children are getting linguistic input, but also input from visual cues, from tactile cues, from kissing cues, from all these different kinds of perception. So the multimodal, multi-layered input provides temporally and spatially coordinated cues. And then the second thing that is really important is that the way that people interact is they are actively and adaptively constructing the communicative environment together. And this is simply for the goal of exchanging information. This is not designed to teach the child language. It's basic, the goal of communicative interaction is to exchange information. But importantly, this seems to structure the children's environment to make learning more easy, learning possible. So my thesis, which I'm hoping to persuade you of today, is a lot of the power, at least some of the power of human learning comes from this very different kind of input, which not only facilitates information exchange, but has the sort of byproduct of helping children learn, particularly the meaning of words. So today I'm going to talk about 3 different studies. Two of them on spoken language. So the first on how gesture supports learning, and the second on how demonstratives like this and that support learning. And then the third study, we're going to look at how signing dyads adapt their behavior in interaction. To see how interaction can help us learn a visual language, not a spoken language, but a visual language. And I'm going to focus on one particular problem here, which is the word reference mapping problem. So just one of the problems that children have to solve, but one which has attracted an awful lot of attention. So this is the reference mapping problem, or the problem of referential identification under uncertainty. And this is Quine's Gavagai problem, which is just basically the effectiveness of word learning depends not just on how often a word is heard, but whether the child can accurately identify the correct referent at the time that the word is spoken or heard. And the problem is that there's usually many, many different objects or many possible referents in any one situation. So how do children converge on the right referent, that when you say doggy, you're referring to a doggy, when you're saying cat, you're referring to a cat, etc. And this isn't just a problem in principle, it's a problem in practice. So Zhang and Yu have found that when children hear a word, they do tend to focus on one referent, but it's just as likely to be the wrong referent as it is to be the right referent. So they're not necessarily focusing on the right thing. And lots of people have tried to solve this problem by positing innate constraints on learning, like the old object constraint, or by positing sort of very, very complex intention reading abilities, reasoning abilities of the infant. But what I want to argue is that actually engaging in multimodal interaction creates shared referential moments, and these amplify the perceptual prominence of the correct reference just at the point at which the word labeling the reference is uttered. So it's the interaction, it's this creation of the interactive environment by the child and the caregiver together creates what we call these ideal word learning moments. And that's what I'm going to hope to convince you of in the next sort of 40 minutes or so. Is that okay? Clear? Excellent. Okay, so let's look at the first study. The first study is on how gestures are used in interaction to support word-object mappings in real time. And this is the brainchild of a postdoctoral researcher at the Max Planck, Yayan Zhang, with some wonderful modeling input from Daughter in the multimodal language department. So Yayan set out to investigate what are the effects of gesture on real-time visual attentional processes in multimodal interaction, and how might these gestures, when coordinated with language, actually help children narrow down the intended referent. And she focused on pointing, and she focused on pointing in book reading. Because although everyone knows you should read with your kids, right? Book reading is a really good way to learn language, but it's actually quite a complex sort of referential ambiguity problem, because on any page, pages in picture books are often quite complex visual scenes. So actually there is this problem of how do you identify the correct referent in books. Plus it's like a book page is like a nice constrained space, so it's quite easy for us to study a book page. So we focused on pointing in book reading. And in this study, and in all of the studies I'm going to show you, we don't do any fancy experiments with EEG or anything like that. We simply ask parents to sit down and, in this case, read wordless storybooks with their children. So this is data that comes from Chen Yu's lab. There's 14 American English children between 18 and 19 months of old and their parents. And they're simply reading these wordless picture books with their children for about 15 minutes, during which some of them got through 5 books, some of them got through 2 books. And what was really nice about this study is we used we tracked the eye movements of the children and the parents using head-mounted eye trackers. So the parent wore one. This is what you can see the system looks like. There's a head cam, which gives us the first person video of what the parent can see. There's an eye tracker, which focuses on the right eye, which tells us where the participant is looking frame by frame or moment by moment. So the parent wore one of these. With a little bit more difficulty, we got the children to wear one of these. And then there were also 3 fixed camera views to capture things, other aspects of the scene, like pointing, which are often not captured by these first-person cameras. Again, here you can see the images that were recorded. On the left, you see the mum's view, the parent's view, mostly mums. On the right, you can see the child's view. The purple crosshairs tell you where the eye is looking. And I just want you to look at how dynamic the interaction is. For example, when a parent names, say the horsey, the parent and the child sort of share a mutual focus on the horsey.
He found a cow. So now he has a cow, a horsey, and a kitty. What else do you think he's going to find? Here he's riding the cow, the horsey, and the kitty are with him. But what's down here? What's down there?
Okay. So we have lots and lots of those frames. We narrowed down the analysis to just the naming events, which I'm going to talk about in a minute. But basically, this is how the data was analysed. So for every sort of different point in each page, I say other people, not me, coded the child's gaze, where the parent was looking, what the child was gesturing at if they gestured, what the parent was gesturing at if they gestured, and whether the parent named and what the parent was naming. So this is sort of manual coded, done frame by frame. There were 1,360 naming instances in this corpus of data, and about 72% of them were associated with a point, right? A point either by the parent or the child. So there's quite a lot of times when there was pointing happening during these naming events. Okay, so the first thing that we looked at was whether gestures structural visual exploration. And I just put this up to show you what the data looked like. So this is an example of a chord diagram. This is one of the naming events. So this is defined as 3 seconds before the name and 3 seconds after the name. So it's a 6-second naming event. And this just shows you what the child was looking at during that naming event. So you can see they're looking at lots of different objects. So this shows the states, which objects they were looking at, and then the lines in between show you the transitions between objects. So this gives you a kind of idea about how much they kind of searched on the page, all the stuff, versus how much they would focus on one object. You can see this visually in these chord diagrams. And what I'm showing you here is sort of 5 different naming events. On the top are the naming events without gesture. In the middle of the naming events with a child gesture, a child point, and on the bottom are the naming events with a parent point. And immediately you can just see from the visualizations that when there's no gesture, the sort of structured search is less structured, right? The search is quite chaotic. They're looking at a lot of different objects and they're transitioning between objects. Whereas as soon as we get a child gesture or a parent gesture, you see a much more focused search just on one of the objects, which is here in blue. So you can see immediately how the gesture use is really structuring the visual search of the child. In order to sort of put some statistics on this, and when I say we, I mean Dota, did some use Markov models to identify the effect of gesture on the child's visual search. So the Markov model basically gives us a way of calculating entropy. And the idea here is that if the entropy is low, this means that there's a more structured search, right? So there's less transitioning to all of the different objects. Whereas if entropy is high, then we have a much more chaotic search pattern, so lots of moving around. So what I'm going to show you is this graph with the graph filled in. Transition entropy is on the y-axis, and the time, the naming event window, 6 seconds, is on the x-axis. And you're going to see how the child's gaze changes over that 6 seconds, with no gesture, child gesture, and parent gesture, with low being good, low being structured. And this is basically what you can see in the results. So the child's gesture is in kind of orangey red. And what you can immediately see is across the 6 seconds, there's much lower entropy with the child gesture. So that indicates a much more structured search with actually, I'm not going to say that, I'm going to say that later, a much more structured search than with the parent gesture in blue, or even with the no gesture. And the statistics, the permutation analysis, I think, sort of bears that out. So you can see on the bottom a global entropy measure and an entropy under the curve measure. Under the curve basically kind of takes into account the dynamics of the eye gaze across the 6 seconds. So it's a slightly different measure of entropy. But in both cases, the child gesture is really structuring the search, right? You are seeing much lower entropy in the child gesture than both parent gesture or no gesture. Okay, so that means that the gestures lead to more structure, but do they help the child narrow down the correct referent of the naming event? So are they looking at the doggy when they hear doggy, or are they always just looking at the cat? So this is what we did next. What you can see on the y-axis is a proportion of target look, so looks at the target, again, across the whole naming event, from 3 seconds before naming to 3 seconds after naming. And again, you can see a very similar thing with the child point in particular, really helping the child, or what's happening in the naming events with child pointing is that the children are looking much more at the target than with no pointing. And also, you can also see the blue line tells you about the parent pointing. And here you can again see more looking at the target, but with a slightly different dynamic. So with the child pointing, it looks like the child is pointing and then the parent is naming the thing. So you get the child looking at the target and then the parent naming it. With the blue line, you see more that the parent names and then the child sort of starts to look at the target, and we get sort of this increase in that. But again, a lot more looking at target than with the no pointing at all. Again, modeling this as a sort of Markov model. Again, I don't want to go into the details, but Dalton changed, sort of revised Frank's intention inferencing framework to model moment by moment reference inferencing. So moment by moment, how confident can the child be based on all of the cues that they're looking at the right reference? So that's what this modeling does. And again, we see the same. So 4 graphs here. I just want you to focus on 2. At the top right, you see the probability of the child looking at the right target. And you can see again a big effect of child pointing in orange, and a slightly smaller but still significant effect of parent, this time of parent pointing on the probability of coming to the true target. And again, entropy under the curve. Again, this time showing that there's more looking at the target, both in the in naming events where the child is pointing, and this time in naming events where the parent is pointing. So the gestures seem to be guiding attention, with the children looking at the intended referent much more during naming. Okay. And then the third thing we were interested in is the timing of gestures. So do the timing of gestures make a difference? And again, you can see the same proportion of target look, but this time on the left, we have when naming is preceded by a point. So somebody points and then says doggy. And on the right, you can see naming with post-label pointing. So you say doggy and then you point. And you can immediately see that we're getting the same effect of pointing, helping people narrow down the referent, but this time we're getting a bigger effect of pre-label pointing. And this is borne out by the modeling as well. So this again is the belief updating. And again, the dotted lines are the ones which are pre-naming pointing. So point and then name. And you can see particularly the child gesture, but even the parent gesture is having an effect. There's much more looking at the target in the context of pointing gestures. So it's not really rocket science to think about, children point or you point and then you talk about what you're pointing about. But what this does is it shows you that really these gestures, so in interaction, multimodal interaction with language and gestures at the same time, you're really helping the child solve Quine's problem, the problem of referential ambiguity. And in fact, there's hardly any referential ambiguity when in the context of when the child points before the object. So we really don't have, in these situations, we don't have a referential ambiguity problem, or it massively reduces the problem. Okay, study 2, we move to demonstratives. So rather than gestures, we're looking at demonstratives. But demonstratives are words that have the same function as gestures. So they are words like this and that in English, or dit and dat in Dutch, or deze, or I don't know what they are in German, probably the same as in Dutch or very similar. But basically, they seem to have cross-linguistically a social function to coordinate attention. So, for example, Yara Ettingen and Rubio Fernandez showed that across 10 languages, they all seem to act as intrinsic attention tools. And they're grammatical words, they're evolutionarily ancient, they're learned early in life, they're documented in all known languages, and they seem to sort of have this function of guiding attention. So look at this versus look at that. So what Yayan wanted to do this time in collaboration with Paula, and again with Dorte providing the modelling work, is to test the hypothesis that demonstratives like gestures can generate word learning opportunities via coordinating the manual activity, the gaze, and the speech, and enable this mapping of words to reference. So how do demonstratives work in this situation? So the same data, the same kind of interaction, just getting kids to play with their parents for 15 minutes, but this time with toys on the floor. And again, data from Chen Yi's lab, from when Yayin was at Chen's lab, and this time with 82 American English, 16 to 19-month-olds and their parents. And again, measuring the eye gaze via the head-mounted eye tracker. So looking at how, first of all, we wanted to know whether the demonstratives were in the data, because you can't learn from something if it's not there. So there were about 10,000 utterances in this data set, and about 10% of them contained this or that. So when you scale that up to the amount of child direct per speech per day, you're getting approximately 30 or 40 demonstratives per hour. So that's quite a lot of learning opportunities if they really do help coordinate attention. Most this and that didn't occur as determinants. So it wasn't look at this dog or look at that dog, right? Most of them didn't occur in that situation. But importantly, between 34 and 47% of the time, the label occurred within a 5-second window. So you'd hear this, and then you'd hear ladybug, or you'd hear that, or you'd hear ladybug. So for example, what's this? It's a ladybug. Well, ladybug, see that? So they were co-occurring with the object names. And they were actually also linked to the spatial location of the objects. So when parents used this, they were referring to things that were close to them. So they would say, oh, look at this ladybug. And when they were using that, they were referring to things that were close to the child. So look at that ladybug. And when you compare this with like look at the dog, there was no spatial relationship there at all. So there was just kind of used randomly. So so these indicate that the parents were using demonstratives from their own perspective, like an adult to adult conversation. So they weren't swapping it. They weren't saying, look at this when giving it to the child. It was look at this versus look at that. And it also indicates that they are kind of providing attentional cues about what to look at. Because if you hear parents say this, you know that they're referring to something close to them. And if you hear parents say that, you know that they're referring to something close, further away from them. We also wanted to look at whether, again, when demonstratives are used, the children tend to look at the target object. So were they looking at the ladybug when they heard this or when they heard that? And again, the answer was yes, they were. So this is the proportion of target looks with this in yellow versus the, like the ladybug, in grey. And then on the right, you have that versus the, that in blue and the in grey again. And you see significant differences again in the looking times. So again, we're seeing a slightly different pattern with this and that. So when parents are using this, the child tends to start looking at the object after the use of this. When parents are using that, they're tending to refer to what their child is already looking at. So in the child's sort of spatial sense. But you are seeing this different. So we are seeing more looking at the target referent with this and that than with the. We also see more joint attentional looking. So this graph shows the moments when both the child and the parent are jointly looking at the referent during this moment versus the moment, and during that moment versus the moment. And again, you're seeing there's lots more joint attentional in these demonstrative contexts. And we know that joint attention is super important for language learning. So this is also interesting. So together, the results suggest that, again, children, these attention-getting linguistic forms, this and that, are coordinating the child and parent's attention to the object that they're talking about. And at that point, very, very often, the object is named during those joint attentional bits. Okay, so demonstratives seem to coordinate gaze to the target objects, but is it actually easier for children to learn from these kinds of moments compared to other moments? So we didn't try and do an experiment with kids, because trying to get kids to learn stuff is notoriously difficult in experimental conditions. So we turned to machine learning models. So here we are now testing the machine chatbots and not the human chatbots anymore. But crucially, what we decided to do was use Rowland et al.'s word referent mapping model, which is called the CBCL model, which stands for Child's View for Contrasted Learning, which is a word I couldn't remember earlier. But we basically fed that model the name, the this instances, the instances, that instances, and the linguistic material that accompanied it. So that's the snowman's hand. Shake the phone. Is this a doll? It was fed these sort of linguistic bits together with the visual scenes that accompanied it. And the question that we asked is, how good is the CBCL model at mapping the correct word to the correct referent in these scenes? And the crucial thing here is this is only data from the child's head-mounted eye camera. So you are seeing the model is getting visual input that the child is focusing on in these moments. Okay? And it actually works really well, relatively well. So all three sort of naming moments, that and this moment, are better than chance. So the model learns better than chance, even with the. But that moment, that sort of events, that events are significantly better than the events. And this events are significantly better than the events as well. And actually, that is better than this. So naming something that's in front of the child is actually better at helping it map the reference to naming something that's in front of you. But the bottom line is that these really do act as attention getters. On the right, you can see the GradCam views. So this is the scenes that the model is learning from, but with the sort of intensity of which areas have a stronger influence on the model's decision about what is being named. And I don't know if you can see in this slide, but basically with this and that moment, the model is much better at kind of focusing on the important bits of information, which here are the doll, than they are in the moment. So in the moment, the model's attention is a little bit more dissipated across the scene, whereas in the that and the this moments, they have clear clues that help it make its decision. So the take home here is demonstratives are like gestures. They bring language and vision into close alignment, creating these ideal moments where the multimodal input is coordinated, and that helps the models and presumably the human chatbots, the real children, effectively map words onto the reference more efficiently. Okay, study 3. study 3. In study 1 and 2, we talked about speaking children and American English children. Like, we're not solving the weird problem there. But in study 3, we moved to signing dyads, so to children and parents who are interacting in American Sign Language. And this poses a really interesting question, because you cannot establish joint attention to an object in the same way in sign language. So in spoken language interactions, you can both be looking at the object at the point it's named. So here, the mum and the child are looking and pointing at the car, and the mum's saying, yes, it's a car. You can't do that in sign language, because you either have to look at the sign or the word. You can't simultaneously look at the sign of a car and the car itself. So these kind of prototypical joint attentional moments where we're supposed to learn language so amazingly just can't happen in sign language. So if this is right and you need joint visual attention to learn sign language, nobody would ever learn sign language. So clearly that's not the case. We all learn sign language. So what PhD student Jenny Sander wanted to do is look at how do signing dyads share joint attention. So given that they learn language, if joint attention is important for language, they must share attention. So she set out to ask, how do signing dyads establish joint attention in sign language interactions? And does this also create sort of these ideal word learning moments? So here we teamed up with Amy Lieberman at Boston University to work with her ASL play dataset, which has 54 parent and deaf child dyads who are basically signing in American Sign Language. And the children, there's quite a wide age range, which has to happen with signing. You know, there's not that many signing children in the world. So we have quite a wide age range here. They're playing with familiar and novel toys, which I'll come to later because that's important. And again, it's just like 12 to 15 minutes playing on the floor. At the same time here, we used the ASL CDI just to see, to get the parents to tick off how many words their children knew and produced, so that we could identify the relationship between joint attention and vocabulary. Okay, so the first problem that we had is that all the joint attentional coding schemes require joint visual attention. So we needed to find a coding scheme that went a little bit broader than that. And Jenny found this wonderful coding scheme by Gabauer and Bortfeld, which allows you to use a whole range of behaviors, to code a whole range of behaviors for establishing joint attention, which kind of makes sense, right? So rather than just looking at an object, you can wave to establish attention, you can tap on an object, or you can use many different kind of attention-giving behaviors, attention-getting behaviors in order to direct attention towards the speaker, or signer, or towards the object itself. So Gabauer and Bortfeld have this wonderful coding scheme which allows us to use many different behaviors to show shared interest, and particularly the most important thing is that these behaviors must be seen to be used, must be coded as being produced with the intention to share attention. So just sort of, touching an object isn't enough. It has to clearly be coded by the coder as that the child or the adult seems to be intending to share attention with this behavior. But it allows us to go beyond sort of visual attention. So I don't want to go into how this coding scheme, which is quite complex, was applied. But basically what we did is we identified the naming events which were accompanied by joint attention of parent and child on the named object, where attention is defined beyond just visual attention. So I just want to give you a couple of examples of what this looks like, because otherwise it's quite tricky to figure it out. So for example, what you're going to see here is a joint attentional episode where the mum gets the child's attention by waving and tapping. The child then looks up at the mum, and then the parent does the relevant sign. So they're clearly sharing joint attention here. And then the child mimics the gesture as well. Okay, and I want to show you another one. So in this one, the child initiates joint attention. So the child raises the orange into the visual field of the mum. The mum gazes up at the orange. The child looks and observes that the parent is looking at the orange, then lowers the orange and signs the word for orange. See that? Go see it again. Got it. Okay. Okay, so both of these examples of successfully establishing joint attention in the signing domain. So firstly, how often does this happen? How often do signing dyads successfully create joint attentional opportunities? Really, really super often. So there were 882 naming events. 81% of them were in what was considered by the coding scheme to be successful joint attention. So you do not need to have visual eye gaze at an object while naming is happening to have visual successful joint attention on the object. The second thing that we looked at is whether these successful joint attentional episodes correlate with vocabulary size in the children. And the answer again is clearly yes. So whether we defined success of joint attention in terms of sort of number of successful joint attentions, or whether we defined it in terms of the length of the joint attentional event, we find a relationship with vocabulary size. So we are seeing lots and lots of joint attentional events are associated with good vocabulary. Whether that's causal or not, I don't know, but they're associated with that. And then what I think is most interesting is that the results show that joint attentional behavior changes first time a new word is introduced. So what was clever about this study, and this is all Amy, this is Amy Lieberman doing clever stuff, not us doing clever stuff. She gave the parents a box of toys that included familiar toys like food and vehicles and stuff, but also completely novel toys for which there is no word in American Sign Language. So these were a dragon fruit, a kiwi, an ostrich, and an armadillo. And as they taught before the session, they taught the parents signs for these new words taken from other sign language. They were real signs, they were just not ASL signs. So they were really, really, really certain that the child could never have heard these words before. So then the question becomes, do the joint attentional behavior change when you introduce a completely new sign? And does this particularly apply to the very first time you use that word? And these results were really, really super clear here. Hang on, I'm going to have to. Okay. Sorry, I've missed the slider and I really wanted to. Okay. I can't do it because I'm on Teams. But basically, what you can't see behind this is that there's a big difference between the first mention and the subsequent mention, and you can see it clearer here. The first mention and the subsequent mention of the completely new novel objects. So the first time a new word was introduced, it was tend to be introduced in very successful joint attentional events. So it was like the parent and the dyad were really clear to establish joint attention before the new word was introduced for the first time. And it also occurred a lot in longer joint attention events. So the signing dyads really seem to be adapting their behavior to optimize learning opportunities in terms of joint attentional events, especially when introducing a new word for the very, very first time. Okay, so those are the three studies I wanted to present today, just to draw some conclusions and then take through three what I think are key outstanding issues. Firstly, drawing conclusions. Compared to large language models, human language learning is super data efficient. It doesn't take us 3 million years to learn language. And I think part of the explanation here is that the kinds of structured interactions in which children learn language massively simplify the inferences that they have to make. So they shape how the learners sample the environment, and they massively reduce referential ambiguity through coordinated cues. It's also important to note that language learning is dynamic. So as we saw, the pre-name points are much more effective than the post-name pointing. So the fact that children are learning in this sort of continuous real-time process, not batch learning, but sort of continually updating their beliefs about what the reference is really important. In interactions that are sensitive to timing of gesture, visual attention, and speech, but are also super sensitive to the affordances of the environment, whether it's a visual language or a spoken language, so that people behave differently. So what this means is that human learning is less reliant on sort of very slow learning of statistical patterns in the input. And it's also less reliant on very complex inferential reasoning that you would normally have to do to sort of solve the reference problem. So I think it requires a shift in our conception of thinking about the input, of thinking about the children as passively receiving the input versus thinking about a very interaction-based, very active input. It just changes the dynamics and the parameters of the learning experience. At least three outstanding questions. What kinds of interactions allow acquisition? So in this big study from 1,001 children from 6 continents that I put on the right, the amount of language input correlates with children's language acquisition across the world. So wherever children are learning, they are being influenced by the amount of input that they're hearing. But some children, like those studied by Riki Fucci, are very rarely spoken to. So they have to learn through overhearing speech. And they do learn through overhearing speech. So this is what they showed in this PNAS paper, that infants who are rarely spoken to nevertheless learn words. So infants learn language by observing interactions, not just by taking part in interactions. So I think we need to think very carefully about how this might be happening. And we need to do the same kind of studies on these children to see if they are also directing their attention to relevant points when they're listening to other people interact. Second thing which I've added particularly for you is how do we learn 2 or more languages at once? And I can't see any reason why we couldn't learn 2 or more languages at once. But again, the affordances of the learning environment are probably changing. The dynamics of the interaction is probably going to be different, especially if you're switching between languages in one conversation. So I think that's a really interesting question. And then the bottom, the sort of multi-million pound question or euro question is what is innate, right? So if you agree that only humans learn language, what enables us to learn from these interactions? In other words, if we gave GPT-5 the same sensory motor abilities of humans to learn from multimodal input, would they learn as effectively? Or is there something special about humans that allows us to learn even more effectively from interactions than large language models? And I put a link to a new preprint that we've just got out where we argue, we argue for a number of different ways to reframe innateness, but in particularly that what's important for humans is this emerging capacity from social action to learn and to take part in social interaction. And that may be one thing that we do need to build into models, this drive to pay attention to interactions. That may be something that is innate. Okay, that's me done. Just like it takes a village to raise a child, it takes a village to do all of these kinds of studies. Yin, Jenny, Dota and Paula, who really drove these studies forward, all of our wonderful collaborators, and obviously the machines and the little humans who agreed to take part in our research. And that's me done. Thank you for your attention. Questions?